Yes, good morning. Here we are at the physics video lecture. Physics 105B video lecture 20. And I was going to start in with the rigid body motion axis not fixed, but there was another topic having to do with the physical pendulum that I decided to discuss. So we're back to the physical pendulum, and this time we're going to do the amplitude dependence of the period. That'll make the discussion very thorough. So once again, as far as the physical pendulum goes, I can start it out this time with the energy and take it from there. Okay, and then we'll get the formula and so forth. So we'll have 1/2 I d theta dt squared, there's our kinetic energy, plus our negative mg d cosine of theta. That's the potential energy, equals negative mgd cosine of theta naught, and that would be the case when, let's go ahead and write this. Theta dot equals 0 when theta equals theta naught. So that's a pendulum that you pulled out, and then you released it from rest. And that's the energy of that. Let's go ahead and draw our physical pendulum again. It's just some extended object. There's an axis of rotation. There's the distance d from the axis of rotation to the center of mass. That would be our angle theta. There's the down direction. And it swings back and forth. Okay, so that much we have. We can also note that omega naught squared is just this mgd divided by I. That's what we had last time, and in fact, if we write d theta dt squared equals 2 mgd over I, then we'll have 2 omega naught squared, and then we'll have cosine of theta minus cosine of theta naught. So we're just gonna, at this point, we would just have a quadrature, but we're going to put it into a standard form. Okay, standard form that I didn't invent. But good. So far so good. We're going to have 2 omega naught squared. Now this cosine theta minus cosine theta naught can be written 2 times sine theta naught over 2 minus sine theta over 2. And I'll show you how that goes. That's just from an identity. So I'll write here, because cosine of theta is the same as cosine of theta over 2 plus theta over 2, right? And then we have the addition and subtraction formulas. Here we would have cosine squared theta over 2 minus sine squared theta over 2. And then we'd have 1 minus sine squared minus sine squared. So that's what we get, 1 minus 2 sine squared theta divided by 2. So we've got that substitution here. And that's where the 2 comes from, and that's why we switch the order theta and theta naught. So now we have theta dot squared equals 4 omega naught squared sine theta naught over 2 minus sine theta over 2. So this we're going to hold on to, and now we're going to define a new angle and a new quantity. So let's define the sine of phi as equal to the sine theta over 2 divided by the sine of theta naught over 2. Because now you can see that phi is going to run from 0 to pi over 2 when theta runs from 0 to theta naught. Okay. When theta is equal to theta naught, we've got a 1 here, therefore phi is equal to pi over 2. Okay, we've got that, and we're going to define this initial sine of the initial angle divided by 2, right? That's like that, as the sine of theta divided by 2 divided by k. So k is identified with that denominator there. It's a constant, right? I'm going to do the initial condition. Now let's go ahead and differentiate, and that will give us, so next, differentiate. So differentiate both sides with respect to time, and we end up with cosine of phi dot equals 1 over k cosine theta over 2, and then times 1/2 theta dot. And this we're going to work around on. We're going to square both sides. Next, square both sides. Square both sides. And so we'll have a cosine squared phi, and we're going to call that 1 minus sine squared of phi. We'll have a phi dot squared. We'll have a 1 over k squared, 1 minus sine squared theta over 2, same move there, 1 minus sine squared theta over 2, and then theta dot squared divided by 4. So let's copy this again, 1 over k squared, 1 minus sine squared theta divided by 2. Now the theta dot over 4 comes from here, right? Theta dot squared over 4 divided by 4 here. We've got omega naught squared sine theta naught over 2 minus sine theta over 2. So now we're going to make use of our new definitions here. Okay. We have 1 over k squared, 1 minus sine squared theta over 2. There's our sine theta over 2 is k sine phi, so it's 1 minus k squared sine squared phi. So we have a 1 minus k squared sine squared phi. With the omega naught squared, and we're going to pull out a sine theta naught over 2. Yeah. Not so fast. Squared. Squared, right? Sine squared. 2 came from. Yeah, let's see how far we. This was all good. Squared, 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 squared. Okay, back to business. So we'll pull out a sine squared theta naught over 2. Sine squared theta naught over 2. And we'll have 1 minus sine squared theta over 2. 1 minus sine squared theta over 2 will be 1 minus k squared sine squared phi. So 1 minus k squared sine squared phi. And this sine squared theta not over 2 is k squared. Okay, so I'm just going to indicate that that's k squared. And now we see we get a cancellation of these two. Let's go ahead and do that. This against this whole thing. Sine squared theta over 2. Not so fast. K squared sine squared phi. One of these should not have the k squared. Real quick here. Minus sine squared phi. Fill this in here. Sine squared phi dot squared. K squared. So oh yes, very good. So when I pulled out the sine squared theta naught over 2, I had sine squared theta over 2 divided by sine squared theta naught over 2. Okay, so that was just sine squared phi. Fantastic. 1 minus sine squared phi. And here we get what we needed, this cancellation, and that one. So what are we left with when the dust settles? Phi dot squared equals omega naught squared 1 minus k squared sine squared phi. So now we've transformed to an equally simple expression, but a more standard form and usable. Good. So now let's go ahead and integrate this. We'll do our ordinary separation of variables and see what happens. That 4 went away, so I think we're in good shape. Yeah. Good. After the dust settles, this we can get rid of. And we have d phi over dt is equal to omega naught root 1 minus k squared sine squared phi. And we'll separate variables. We want to find the time anyway. What we're looking for is the period of the pendulum, and we're almost there. So we have dt is equal to d phi, I'll write 1 over omega naught d phi over root 1 minus k squared sine squared phi. And we can, of course, integrate both sides. And write t integral dt 0 to phi, put a little prime there, and we have time as a function of angle. Now this is actually a standard form of an integral. So let me pull the 1 over omega naught out. This thing here gets a name. Phi prime 1 minus k squared sine squared phi prime. So this is an elliptic integral, and it is the incomplete elliptical integral. Incomplete elliptical integral of the first kind. And what letters are we going to call it? F of k and phi. First kind. So this is its title. These things are functions. 1 over omega naught f of k and phi. Okay. So these are tabulated functions because you can, you may not be able to do this in closed form, but you can tabulate it. Okay. So you could actually look these up, and they would have tables of them. Nowadays they're on a computer as well. Elliptical integral, first kind. So that's time as a function of angle. What we want is the period of the pendulum. So the period of the pendulum, because of the way we defined k here, which is right here, maybe I'll leave it on the board. Because of the way we define k, the period of the pendulum will be, I'm going to erase this, will be 4 times this integral if we integrate from 0 to pi over 2. That'll follow straight from this definition here. And so period t, so we'll have t, because if we integrate from 0 to pi over 2, that's the full amplitude of this thing, full theta naught. And for the period, it has to go one way over to the left, all the way back. So it's 4 of those. So period will be 4 divided by omega naught integral 0 to pi over 2 d phi root 1 minus k squared sine squared phi. And we have k and phi and everything defined right here, so we'll just hold on to this definition or rewrite it at the appropriate point in your notes. And this also gets a name. This is, what letter are we using here? This is capital K of lowercase k, and that's the complete elliptical integral of the first kind. And again, you could tabulate these, as we'll find them tabulated. The first kind. Okay. Now, what would this function look like? Should we just view this integral and get a feel for the function? Okay. What would its graph look like? Okay, we're just going to wing it here. K of k. Okay, so when k is equal to 0, okay, k is equal to 0 means theta naught is equal to 0. So it's a limit of the small angle approximation. So when k is equal to 0, we just have 1 d phi from 0 to pi over 2. Okay, so that integral is just equal to pi over 2. Furthermore, yeah, when you take that pi over 2 and multiply by 4 over omega naught, you get 2 pi over omega naught, which is, of course, the small oscillations period right? Small amplitude period, so we're in good shape right there. Now, what does this integral do? When k approaches 1, when k approaches 1, that's when theta naught approaches 180 degrees actually, okay? Theta naught of 2 would be 90, sine of 90 would be 1. So theta naught approaches 180 degrees. So physically you're standing that pendulum on its head, so to speak. And if you could balance it perfectly, it would have a period of infinity because it would never fall down. Okay, it would start infinitely slowly. So we would expect that integral to diverge. So that would be something to look into if you like to investigate integrals like this. Could you prove that it diverges? Here, I'll just, okay, so that would be a fun task. What I want you to do for the homework though, is the small approximation, the approximation for small values of k squared sine squared phi, okay? And of course, when you want to put sine squared phi in, okay, I'll actually give you a couple more hints there. So we have everything here. Yeah, I think so. Okay, I'm going to send this up, and I'll formulate this problem here. So the point is, the finite amplitude period in the limit of small amplitudes, that's what we expect, okay, because 4 over omega naught pi over 2 equals 2 pi over omega naught, check. Now, if you make the amplitude greater and greater, we actually expect this asymptotic version. So it's going to be, increasing function of k, and k is an increasing, function of theta naught. Okay. So let's go ahead and just formulate the homework. So you can do a lot of things with this, but we want to get the next approximation. So homework is to expand the integrand. So what we're going to look at is 1 minus, let's just call it x to the minus 1/2. And that'll be 1 plus 1/2 x plus and so on. So go ahead and do that with the, that's a standard expansion, but you may as well do it with the Taylor series and get the first terms, or maybe get the second one as well. Get the next one as well. We're not going to use the next one, plus question mark, but it's good to have it there, okay? This is for small x. And of course, what we're letting our x be equal to is the k squared sine squared phi. Okay. And then I'll just put the answer here so that we know what we're working towards. Show that the period goes as 2 pi over omega naught times 1 plus theta naught squared over 16 plus and so on. So if you expand this integrand and start integrating, then your next correction will turn into this. Okay. And this is a worthy result. So we were talking about the physical pendulum, and at the beginning of the discussion, or last time in the discussion, we were finding corrections, for example, for the physical pendulum that's, you know, basically modeling the ideal pendulum, but you have a finite sized bob at the end here, and it's going to give a slight correction. Okay? And here we're going to find the correction to the finite amplitude. Okay. And so this is actually the non-linear pendulum. I should have mentioned that, right? The small amplitude approximation turned the sine of theta into theta in the differential equation, or it turned the cosine of theta into theta squared over 2. 1 minus theta squared over 2. And here we have a general result. So this is good for arbitrary amplitude, and this is the next correction to the period. 2 pi over omega naught. And yeah, I had that omega naught squared. Omega naught squared was mgd over I. Make sure you remember where that came from. Okay, so then you'll have a good view of the entire physical pendulum. I gave us a like a couple of homeworks, I think, last time to deal with that. So that'll be good. This, okay, I think that's all we're going to do today. It's a good place to stop. Yep, it's a short one, that's okay. So we have done some fixed axis rigid body motion. Physical pendulum is a good application, and we have some, a little more depth to it. This whole theory of the physical pendulum, by the way, is very developed because the best timepieces were once physical pendula, and everything possible had to be known about them. Okay, next time we do rigid body motion, non-fixed axis. But for now, we'll leave it at this. See you guys next time.